talk about container. We hit on that during awareness, but we're gonna go a little more into depth about what to how to identify what to expect. Yes.
So when we were watching that video and they're going over all the tanks, like almost all the tanks were in the ERG.
Mhm.
So the ERG has most of the tanks in the UOC.
We're gonna go over bulk storage tanks, cargo tanks, tank cars, markings, intermodal containers, ton containers, pipelines, transport, and then bulk and non-bulk containers. They all have their different characteristics and will behave differently. So understanding that will help us determine how we respond. Why do we want to know what type of container we're looking at? Where you're going with? Yeah, exactly. So you have a very sturdy, heavy duty container. What do you think that would indicate? Could be high pressure.
Maybe it's cold, thermal regulated.
It's probably going to be something that is pretty dangerous. So the more dangerous, the more reinforced that container is going to be. Okay, so 4 major types of containers. We've got pressure containers, cryogenic containers, solids holding containers, and liquid holding containers. Just as any incident we respond to, everyone's unique. There's no, you hear people say that's our bread and butter. There's no such thing. Everything has its own hazards and idiosyncrasies. Okay, so if you look at this table 5.1, which you can find on page 180, 181, it talks a bit about the different containers and their releases, stressors, breaches, and dispersion pattern. So I'd like you guys to take a look at that. We're not going to do it right now, but you can go back and review that to get kind of a general idea of what you'll be dealing with. What are the 4 major container types? Pressure? Pressure. With liquid holding? Solids holding. Okay, good. What are you gonna find in a pressure container?
Gas.
That's for liquids. What are some of the characteristics? Yeah.
Bolted covers.
Okay.
Pipes and valves.
These are the ones that are dangerous to us, yeah. All right. Different stressors, all 3, so thermal, chemical, or mechanical. Just know that you can have a failure long after the damage has occurred. Excuse me. We might have releases from the pressure relief devices. Runaway cracking, which can lead to what?
Flooding.
Puncture, splits, tears, not as common. But we could have accidents, especially during transport. So pressure container releases can happen through the rapid relief valve or damaged attachments and fittings. Typically, they'll activate 75% of the test pressure. Let's show you a quick video here. Zach, you want to see it again?
Yeah.
Yeah, some of these have been around for 100 years.
Zach. Imagine coming home to that.
Yeah.
Okay, different dispersion patterns. Hemispheric. What does that look like?
It's on the ground and so.
Yeah, so attached to either the ground or the water, and it comes up kind of irregular. With a cloud? Okay. With a plume?
The mushroom cloud.
But not all of them.
Okay, and then what is a characteristic of the plume? It's affected by what? Right? Wind, yeah, wind, topography. Okay, what's a cone look like?
It's like small to big.
Looks like a cone.
You could say.
Yeah. Yeah, extreme caution when handling pressure containers that have been involved in an accident. Are they likely to fail?
Mechanical, human, animal.
Okay, containers, what's held in cryogenic containers? Plus
Refrigerants.
very, very cold. So here's a picture of it, but I found a video that I thought was very helpful. Which I'll show you here in next couple slides. So if you have a breach, where that stuff coming out is so far and cold that it can be very dangerous. You can have chemical stresses from the exposure from the of the chemical, and then an accident. Yeah, go ahead.
So just a quick question. So with our PPE, we have a max heat that we can go to. Is there like a max coldness before it's like? No.
You know what? That is not something I have thought about. But let me find the answer for you. And I would not count on it to protect you from the extreme cold. But that is a really good question. So venting is a function of some cryogenic containers and might not mean it's failing. Oh, what the heck happened? Very nice looking family.
I think the one on the end got cut off.
I would not like her. Got her right out. Okay, I'm gonna have to open the back of eye and make sure what
I should
happened.
have cut off by your family and it's just do a PowerPoint.
Okay. Cryogenic containers can have any type of breach. Could be the relief devices, damaged fittings, punctures, splits, tears. This video actually, it is, I think, about 15 minutes, and I find it valuable. It kind of shows you what the container looks like more so than the picture, and we'll also show you some of the damage. We're gonna watch half of it, just about 10 minutes of it.
Nitrogen is widely used in research facilities around the world. Liquid nitrogen can freeze biological tissues for storage or cool a system or chemical reaction. Always remember, there are real and significant hazards associated with the use and storage of liquid nitrogen. In this video, we will discuss the hazards associated with liquid nitrogen, parts of a liquid nitrogen tank, including the safety features, safely dispensing liquid nitrogen and handling cryogenic tubes, filling a liquid nitrogen tank at a dispensing facility, and what to do in an emergency, safely transporting liquid nitrogen within a building, other cryogenic liquids requiring additional safety considerations. There are three primary health and safety hazards associated with liquid nitrogen. Extreme cold. Liquid nitrogen can cause instant severe frostbite to skin or eyes. A jet of vapors can freeze tissue faster than liquid or metal contact. Proper use of personal protective equipment can help prevent exposure. This includes a lab coat, safety glasses or chemical splash goggles, and a full face shield, protective gloves specifically designed for use with cryogens, sturdy shoes that cover your feet, pants without cuffs that could trap liquid next to your body.
Always remember to wear PPE when removing or handling cryotubes and cryotubes that may be filled with infectious material.
Extreme cold can also change the nature of materials. It can make some rubber or plastic materials more brittle and allow them to break easily. To prevent breakage, use only materials designed for use with liquid nitrogen cylinders and attach only transfer hoses designed for liquid nitrogen. Asphyxiation. Large spills of liquid nitrogen can immediately displace oxygen, especially in poorly ventilated areas like cold rooms. Since nitrogen is odorless and invisible, fill and store nitrogen containers in well-ventilated areas. Contact your safety office to determine if a space where liquid nitrogen will be used or stored is well ventilated or may require oxygen depletion alarms. Expansion. Liquid nitrogen can expand up to 700 times when changing from liquid to gas. Rapid changes in temperature can result in rapid or explosive conversion to gas. Rupture incidents have occurred in university laboratories after users had inadvertently altered or obstructed safety relief devices, or tanks became dented and compromised. Pipes, vessels, NMR tubes, and cryotubes with trapped liquid can violently rupture, causing injury and exposure. Avoid storing liquid nitrogen tanks near heat sources with direct exposure to the sun or in locations where the temperature can fluctuate widely. Consult the tank manufacturer's operating manual and get familiar with the functioning of the tank valves and piping circuits. A typical liquid nitrogen tank has multiple pressure relief valves. Never obstruct, block, cover, or tape a pressure relief valve.
If your cylinder vents loudly through the relief valve, is cold to the touch, or has frost buildup around the pressure relief valve, leave the room and contact emergency services.
Know your liquid nitrogen tank. Liquid nitrogen tanks are typically 1.5 meters tall, 50 centimeters in diameter, and contain 100 to 160 liters of liquid. Tanks consist of an inner and outer vessel. The vacuum space between the two vessels acts as a highly efficient thermal barrier. Special materials inside the vessel maintain the vacuum for several years. These portable liquid nitrogen tanks are specifically designed so the liquid nitrogen is safely insulated to ensure users are well protected from the extreme cold during handling or transport, and the user can withdraw the contents either as liquid or as gas.
If the cylinder is dented or damaged during transport or use, the tank must be professionally inspected to ensure it may continue to be used safely.
Cylinders are equipped with pressure relief valves that will open and close to release gas at preset pressures. The primary pressure relief valve opens at the lowest pressure and regularly vents excess gas. A slight hiss from a liquid nitrogen tank indicates normal operation of the primary pressure relief valve. A small gauge installed on the cylinder may show the pressure inside the tank. This gauge reading should be equal to or less than the setting of the primary pressure relief valve. The secondary pressure relief valve is set at a higher pressure. On this tank, this valve is installed on an extended stainless tube to ensure its opening if the primary relief valve is blocked by ice buildup or fails in any way. If both relief valves fail or are not able to handle the pressure, a burst disc at the bottom of the tank may blow out and vent the pressure to prevent a tank rupture. The primary and secondary pressure relief valves on this tank are set at approximately 20 psi and 50 psi. Other liquid nitrogen tanks may be rated for higher pressure settings. So be aware of the specifications for your tank. Do not remove or tamper with any of these safety devices or their protective covers. If your research group owns a liquid nitrogen tank, it is your responsibility to maintain the tank in good operating condition.
If there are unexpected leaks from your cylinder, valves or O-rings may require maintenance. For assistance, contact the university staff member responsible for the liquid nitrogen facility.
Dispensing liquid nitrogen. Liquid nitrogen tanks should always be stored and operated in areas with plenty of ventilation. Liquid nitrogen tanks must always be stored and operated in the upright position.
Operators should never block, plug, or attempt to repair anything on a liquid nitrogen tank containing liquid. For assistance, contact the university staff member responsible for the liquid nitrogen facility.
Always wear appropriate personal protective equipment before withdrawing liquid nitrogen liquid from a tank or withdrawing cryotubes. Depending on tank style, there may be 4 different piping circuits on a liquid nitrogen tank: the liquid dispensing circuit, the pressure building circuit, the economizer circuit, and the gas use circuit. Consult the tank manufacturer's operating manual and get familiar with the functioning of the regulators, valves, and piping circuits. For dispensing, connect a manufacturer-approved transfer line for liquid nitrogen. The natural evaporation rate alone is often not capable of providing enough pressure. The tank pressure can be boosted by the pressure builder circuit with which most nitrogen tanks are equipped. Pressure builder styles may vary. The pressure builder regulator and pressure builder valve adjust when liquid nitrogen is introduced to the pressure building circuit. Liquid nitrogen in the pressure building circuit is turned to gas and delivered back into the top vapor space of the tank. This increases the pressure inside the tank, allowing the liquid from the bottom of the tank to be delivered to the liquid valve. Keep in mind that opening the pressure builder circuit will not immediately increase the pressure inside the tank. The pressure building process may take several minutes. Become familiar with the different cylinder pressure builders you may work with. Once a pressure builder regulator is set, it should not be changed. Transfer of liquid at high pressures can
Kind of shows you the ins and outs. And here's some expansion ratios of common cryogenic materials. Look at the boiling point of nitrogen, -320, and then the expansion. Pretty impressive.
Isn't that liquid nitrogen the stuff we use to like freeze off the wood?
Yeah. So I think we can do that. Different dispersion patterns. Atmospheric fluid, wow, cool. What's the liquid holding container?
A cylindrical. And with
Could be. Anything to hold the liquid? What are some examples?
could be an intermodal transport container.
Like a gas can. Okay. Drums. Drums, yeah. What's that?
I was thinking like carboy.
So be thinking, there's a wide scale of different types of liquid holding. So it could be a tank car, it could be a glass bottle. Could be, something carries something that polymerizes. All right, so, dispersion patterns that are common, the streams of pools. Oftentimes those liquids might release vapors that act like gases. And know that, different materials will have different dispersion patterns. Okay, common dispersion pattern for a liquid container? Stream or pool? Okay. All right, how about a solids holding container?
You could, a mixed cargo train.
Okay,
Or sea containers.
The rectangular.
so it's gonna depend on, what it is. Coral mentioned that drum for liquids can also be used for solids. Typically, those are damaged by mechanical stressors. Where, we're seeing, it's not under pressure. And you might have a reactive material. So we're looking at breaches that might include punctures, splits, tears. And you also have pneumatic loading and unloading attachments could be damaged. What are we gonna see? Spills and leaks, detonation. If you have oxidizers, peroxides, explosives, or water reactive. Clouds, cones, irregular dispersion. Okay, so how are we gonna damage our solids holding containers?
Mechanical.
That's just a common cold storage. So a pressure tank, I probably need to know this. It holds things in pressure at 15 psi or higher. So you could have relief, like a rapid relief event. You could have a slow leak, or you could have a violent rupture. Found in pressure tanks, flammable, toxic, corrosive. I think we've touched on levies pretty extensively. I don't think we need to go over that again. So what happens? They expand rapidly and displace oxygen. Why is that a problem?
That creates a simple asphyxia.
Okay, cool. And then what do we know about gases?
They travel long distance.
Yeah, and so then we have a problem like if you have a toxic gas, travels a long ways. That's a lot of people that could be affected. So here's a couple types of your pressure vessels. You got your horizontal pressure and then your spherical pressure. Some of these can hold a high volume of material. Just be aware. How does that play in? Think about your response.
For the distance you have to isolate, so if you have this, like, you got that spherical pressure vessel. If that thing is about to go boom, you don't want anyone or anything near that.
Well, the quantity could potentially have a significant impact on how you respond to it. Okay, so what's the pressure in a pressure tank?
About 15 PSI.
Okay, good. They have cryogenic liquid tanks. They will also have 15 PSI or greater. Some of these hold quite a bit, 300 to almost 500,000 gallons. They're gonna be built the same way, the insulated, vacuum jacketed, safety relief valves, rupture disc. Different types of things they might store. How do we know what this one is? Because it says, we can tell what it is by the way it is. This is kind of mind-boggling. From the newer liquid natural gas, 30 to 60 million gallons. That's a lot. Okay, what do we know about cryogenic materials? Very cold. And how are we gonna find them?
Looking for frost.
In like the summer, when frost. There be frost, even in cold temperatures, you won't see frost because that stuff comes out, it is cold. The release will tend to pool. You might see them as a fog or a cloud. And they will displace oxygen in potentially explosive environment. Still a hazard even if you don't see it. Okay, liquid oxygen leaks on asphalt and may get shock sensitive and. I'm gonna show you another video. I just thought it was kind of cool. So we're gonna pause here while I pull that up. You have cryogen released from this container. What are you worried about? Freezing. Freezing? Okay.
Flammability.
What's that?
Flammability.
Okay. Asphyxiation. I mean, asphyxiation isn't good, but your answer was good. Okay. Low pressure. So know these numbers as well. So a pressure is how much? A pressure tank 15 or more, okay, and so a low pressure would be 0.5 to 15. So you might have a dome roof tank, spheroid tank, noted spheroid tank. Typically you'll find flammable combustible liquids where they can release products as liquid gases or vapors. So you want to make sure you don't have an ignition source. I hope I'm not saturating you guys with videos, but I had another video of a pressure storage tank fire, if you want to see that.
Yeah.
Of those low pressure storage tanks. That's also in your book.
Oh. High pressure is the one that had like grounded on this, and that's interesting.
Yeah.
Well, this one looks like an oval circle. Not like
An oval circle.
Yeah, not like a true like.
The awareness test?
Why do you want to eliminate ignition sources?
So whether spilling or leaking does not.
So it doesn't go boom?
So do it.
So what do you think the pressure is on a non-pressure? So it can be non-pressure or atmospheric storage tank? What's that?
0 to 0.5.
There you go, less than 0.5. So anything after 0.5 is going to be a non-pressure or atmospheric pressure. So they're gonna, might have a horizontal tank, lifter roof tank. Ordinary cone roof tank, vapor dome roof tank, open and closed floating roof tank. Those floating roof tanks, the way those work is the roof moves with it. And the intent is for one, to reduce like evaporation, but also to reduce that explosion risk, right? So you're not trapping. They could be corrosive or toxic. Also in your book, 190, 191, be a good idea to look through those. I would imagine something will be on your test. So if they're damaged, they're going to spill or leak through their walls, valves, fittings, attachments. Also know that your vapors may travel quite a ways. I'm sorry. I'm going to like that. Yeah.
Don't you wonder what's in the other stuff?
I know.
Cause you're all like, even that first one.
Those are dangers. You have to be trained at a confined space. If you're gonna go in there. So there's a question here. What can cause water in the bottom of a non-pressure atmospheric storage tank to boil and expand more than 1,600 tons in volume? So if you go to 192. To read that.
Sorry, which part?
So the third paragraph down.
With certain types of fuels, crudes, and some other heavy oils, there may be potential for boilovers, frothovers, and slopovers. For example, crude oil storage tanks normally contain areas of stratified water within the crude oil and a layer of water at the bottom of the storage tank. Due to the difference in density between oil and water, the water's higher density causes it to sink to the bottom of the tank. This water creates the potential for disaster at crude oil storage tank fires. When a fire occurs in a storage tank, residues from surface burning become denser than the unburned oil and sink, forming a hot layer. When this hot layer or heat wave reaches the water in the bottom of the tank, it causes the water to boil and expand more than 1,600 times in volume. The expansion of water forces the layer of oil upward and out of the tank, resulting in the discharging of burning oil onto a large and uncontrolled area outside of the container, overflowing the tank.
That's kind of scary. It kind of looks like that's what happened in that video. Okay, underground storage tanks, so do we have those around here? No, I sure do. They typically gonna be built of steel, fiberglass, steel with fiberglass coating. Typically, you're gonna have liquids such as gasoline. And some of these are going to be buried. And so you can identify them with some of the valves and such, that's, above ground. So it'll either be low pressure, which is how much?
0.5 to.
Okay. Or non-pressure. 0.5. So some clues here. So here, you got some vents. You might see like residential, but a hazard is some of them have been abandoned. And they might be leaking. And we don't know it until they end up leaking into a place we don't want them. So what's the hazard with those? Okay, so how do we, just to recap, how do we know?
By the valves and openings you can see on the ground,
What's that?
by the valves and openings you can see on the ground.
Yeah, so the vents or valve, yeah. Okay, you've been at it. Let's take a quick break. And then we'll carry on through lunch. Or up until lunch, I'm sorry.